A polyprotic acid can furnish more than one proton. A polyprotic acid will always lose one proton at a time, unlike bases which will lose all their hydroxides since they're ionic. The acid gets weaker for each proton it loses. So the Ka1 is always greater than Ka2, which is always greater than Ka3. When you look at your Ka table in the back of your book, you'll notice that you have Ka1 values, 2, and 3. And so for ascorbic acid here, we can see that we have 10 to the negative 5th and then to the negative 12th. All of our Ka1 values are going to be larger than the respective Ka2. And if there's 3 hydrogens attached to it, then there's going to be a Ka3, and that's going to be even weaker than the other 2. Monoprotic acids have 1 acidic hydrogen, or proton. Diprotic acids have 2 acidic protons, and triprotic acids have 3 acidic protons. When calculating the pH of diprotic or triprotic acids, really the only Ka we care about is the first Ka if we're trying to calculate the pH. So let's go ahead and solve this problem, and we'll see why only that first hydrogen that comes off matters. Step 1 would be write our dissociation equation. Only one hydrogen can come off, leaving us with HS negative. Just like before, we would set up our rice table. And then plug it into our equilibrium expression. For our equilibrium expression, we need to use Ka1 because H2S hasn't lost any hydrogens yet. Our Ka1 is very small still, so we can't ignore that minus x. So multiplying and then square rooting, I get that my x is equal to 1.14 times 10 to the negative 4th. So now we can do the same thing with HS, because HS also technically will produce a proton. So HS is going to give off a proton and then turn into S negative 2. Unlike this first one, we started with 0.1 of H2S, but HS is X, and my X was 1.14 times 10 to the negative 4th. But unlike the first one, we didn't have any H to begin with, but when H2S broke apart, it produced some hydrogen, which was also X. So unlike the first ice table we did, we should have some H already in the container from when H2S broke apart. But we don't have any sulfur because H2S didn't produce S negative 2. Just like before, we're going to set up an ice table. So the HS is going to produce some more hydrogen and then some sulfur ion. We can plug that into our equilibrium expression. This time we're going to use Ka2 because Ka2 is for H2S when it loses one hydrogen or becomes HS. This time my X is even smaller because my K value is even smaller than it was before. So I can definitely ignore my minus and plus X's. And in this case, I have the same numerator as denominator, so those also actually cancel out. So my X is just equal to 1 times 10 to the negative 13th. So to calculate the pH, I would need to do negative log of my hydrogen ion concentration. Well, hydrogen is technically 1.14 times 10 to the negative fourth plus x, which is this very tiny number. 1.14 times 10 to the negative fourth plus 1 times 10 to the negative 13th is still going to give me 1.14 times 10 to the negative fourth. That's why if the question only asked calculate the pH of a 0.1 H2S solution, I really only needed to do this part over here and then negative log the 1.14. Doing all of the step in pink wouldn't help me with my answer because I'm going to produce such a small amount of hydrogen that it's going to be negligible, that addition. So my pH, I'm going to say, is negative log of 1.14 times 10 to the negative fourth, which will give me 3.94. When you would need to do the pink step is if the question had said, what is the concentration of S negative 2? So if that's what our question was, then I would have needed to do this pink step because my S negative 2 is what X is in the pink part over here. So this is equal to my S negative 2.